Alright, students, we'll do a very quick debrief on the spectroscopy exercise 1. The main focus will be on the thought process. So those parts on recall, I guess I will skip it and you might want to review it on your own. Okay, so the very first thing I think we need to do is to determine the degree of unsaturation of this compound X. We are given this particular formula C12H19NO. So if you do a quick calculation on the degree of unsaturation, even if you don't remember the formula per se, it's quite easy to derive it because number one, we need to look at the maximum number of hydrogen that a 12 carbon can have. So that's 2n plus 2. So that will be 26. And then we need to subtract off the number of hydrogen that this compound has, which is 19. Okay, and then we need to add one more. The reason why we need to add one more, right, is because and we don't care about oxygen, is because nitrogen forms 3 bonds and oxygen forms 2. Yeah, so potentially any compound which contains nitrogen, right, for a fully saturated compound, there will be one extra hydrogen as compared to one that is not fully saturated. As compared to one that is only carbon-based, carbon and hydrogen-based. Okay, so in that case, if you do a quick calculation here, you'll get 4. Okay, now 4 is a very nice number. Yeah, because if you get a degree of unsaturation of 4, usually we will think about aromatic system, aromatic ring, because a phenol ring gives you a degree of unsaturation of 4. Okay, well, it might be a combination of ketones, ester, aldehyde, etc. But I think without further analysis, and usually we are given, say, the IR or the NMR. I think from whatever we are given, we can do a full analysis and realize that usually it contains an aromatic system, which is a phenol ring. Okay, so now we are given the IR. So I think first of all, we might want to maybe assume that it's a phenol ring first, because I think if we look at this particular region where it's about let's say about 1500, okay, this particular region, right, there is actually very sharp and strong stretches. So normally we associate this with the CC aromatic system. So it's the C-double-C stretches in the aromatic ring. So that kind of like give us a telltale sign that we might have some we might have one aromatic ring present. And of course, if you are sharper, you can see some overtones here. Yeah. So these overtones are usually very characteristic of substitution pattern in a phenol ring, which of course within our curriculum we don't go into details. Okay, so I think with this idea we might want to make do with a aromatic ring first, and then if you look at the IR, so we look at the IR. Maybe usually we want to look at the IR by actually splitting the part, drawing a line across 3000. Yeah, so we notice a peak here. Yeah, so this particular peak, well, it may be due to OH stretch, or it may be due to an NH stretched. But if you look at the region, that's probably found at around 3000 to 3003. So if we switch to over here, yeah, you get actually kind of like a weak signal, NH stretches, so which is between 3300 to 3500. If you're thinking about maybe hydrogen bonding OHs, well, that is possible. That is, of course, one possibility that you can think about as well. Okay, yep. Then anything below all this, all these peaks here and there, well, we are expecting a series of sp2ch stretches that's above 3000s, and sp3ch stretches that's slightly below 3000 per centimeters. Okay, so with that, you need to kind of like formulate some ideas on what are the potential groups that might be present. Okay, so if we look at our choices here, okay, you are supposed to kind of like make some choice. You know that you can't have a primary amine. The reason why you can't have a primary amine, right? Well, it's because if you have a primary amine, then you are expecting 2 weak signals, but we only have one here, so probably not a primary amine. Definitely no, not carboxylic acid, and not ketones, not amides. Okay, for a very simple reason, because they will burst the degree of unsaturation, and you don't have a CO, strong C double bond O stretched. So definitely we are not looking at these two. Okay, if you have amide, ketones, or carboxylic acid, you expect one more degree of unsaturation, which is obviously not present. Okay, and ether is possible, and ether is possible. So that's a possibility that we are looking at. Of course, a phenol ring. Okay, what about a secondary amine and an alcohol? Okay, so well, I mean, if you look at the region, a secondary amine might tick the checkboxes, the checkbox. What about alcohol? Well, I mean, it may still be possible, but I think we need to do further analysis. So in this case, if you want to do further analysis, the NMR do might give you the biggest clue ever. Okay, so if you take a look at the 1H NMR, which I think after the teachers remark through the scripts given by the club, given by our students, right, we realized that a lot of the answers are relatively weak in deduction. Okay, so remember that there are 3 ingredients you need to provide in your deduction. I think the first one is you need to indicate to us the multiplicity. Okay, so the multiplicity is of extreme importance here. So in this case, I'll just do a quick one, and then I'll leave you to see, like what are the possibilities out there, and then you realize that the answer is quite restricted. Okay, so number one is we need to look at some obvious region. If you need the data booklet, you can always refer to the NMR signal, but as I often share with the students, these NMR signals, somehow they do you more harm than good. Okay, so we'll just do it directly from here. Okay, so now we have signals close to 7, 3 of them, multiplets. So these are things you need to include in your answers. Multiplets, integration ratio 3, and then what else? Yeah, multiplet, and then near the aromatic region of 7 plus. So you would expect this particular signal to be due to the aromatic protons in the phenol ring. And based on the degree of unsaturation, which is 4, so there can only be one phenol ring. Okay, so from here, right, when you write out your deduction, right, you shouldn't simply just write it's a tri-substituted phenol ring. Okay, you should actually give a little bit more details as well. Like for example, 3 aromatic protons are present due to this multiplet over here. Then it is likely that my compound is a tri-substituted phenol ring. Something along those lines, I think it helps a lot. Okay, so we have a phenol ring. Okay, that is tri-substituted. So I'm just going to call this X. Okay, I'm just going to randomly place the groups because I don't know how they are arranged. Y and Z. Okay, now remember that problem solving is a very important skill that you need to develop. Okay, so what I often share with the students is that I think the first thing that you might want to think about is, okay, am I able to get the molecular formula of the ring out from here? Okay, so this particular ring, right, it has a formula of C6H3. Okay, of course I don't know what are my X, Y, and Z. Sorry, I think I put here Y again. Yeah, X, Y, and Z. I don't know what are they, but it doesn't really matter here. Yeah, so I just need to do a subtraction. Okay, so from the formula given to me, which is C12 H19NO, right? I will subtract away C6H3. So if I perform a subtraction, I'm going to get C6H16NO. So that means that my remaining XYZ groups contains all these atoms. I think having a sense like this, right, it really helps you a lot in elucidation, because it kind of like places you on safe zones, like you don't feel so not so confident about it, and you know that you are always in control. And of course, there is this little broad singlet here. This is often described as a broad singlet, so it looks like this, so it's a broad singlet. Okay, so this particular broad singlet, right, actually is definitely due to the labile proton. Okay, so it's a labile proton. It could be OH, it could be NH, but we're going to see. Okay, we're going to see. So once we analyze more, then you realize that it's actually more likely to be a secondary amine than anything else. Okay, I think we need to perform more analysis so that you probably will become a little bit more confident. Okay, now another very important characteristic that I want all of you to look at is always look at singlet peaks and with 3 protons. Okay, so for example, the signal at about 3.8 thereabout or about 3.3. So these are very sharp singlet. So it signifies a CH3, okay, bonded to a highly electronegative element. That's called A. Okay. Now, truth to be told, right? Your compound has only O and N. Agree? Your compound has only O and N. So definitely your A has to be either O or N, right? So in this case, if you have done enough question, you realize that actually 3.7, 3.8, it's usually a methyl group bonded to oxygen. I mean, it's not always the case. You can have exceptions, not an issue. But generally, if you work from there, you realize that if you want to look at a CH3, which is relatively desuted, so we are looking at O methyl. Okay, this is OCH3. And then maybe for now, let me postulate this to be an NCH3. Okay, NCH3. I think it does help a little bit when I perform some postulates here. Okay, then let us see other potential signals and telltale signs that allow us to finally get our answers or our proposed structure. Okay, we do see 2 quartets here. So that's at about 4, which is very distributed, you know. Like it's quite uncommon for you to get such a distributed quartet. Okay, and then we have another quartet here, okay, which contains 2 hydrogens. Okay, now I think right now, right, it is timely for us to do some pairing. Okay, so let me ask you a question. How is it possible that you can get a quartet, right, with 1H? Like. Okay, so to get a quartet with 1H, right? So basically, I must have a CH, of course, just 1 hydrogen, right? Okay, then I must, this carbon must be bonded to a CH3, agree? Because so that it can be splitted into, it can be splitted into a quartet. And then the other 2 groups, right? Okay, will not actually cause the hydrogen to split. Yeah, will not actually cause it to split. And then, so these are groups, okay, I just put a question mark here. These are groups that will not cause the H or the CH3 here to split. And this actually makes perfect sense. Okay, let me erase this first so that you guys don't get so confused. Because I would expect this CH3, right, okay, to be split into a doublet, which if I were to look at the NMR, I have a doublet here. So that's just nice, like it's a match. Both of them is a match, you see? Yeah. So therefore, I'm going to postulate a potential, maybe a likely bonding pattern in my compound. A likely pattern. I mean, it's not always the case, but I'm going to postulate something likely. Okay. So therefore, right, if I want my chemical shift of that proton, of that sole proton, right, to be at 4, okay, and with the given electronegative element, do you think it can hit 4? So some of you are thinking, Ken, let's put oxygen. You get what I'm trying to say. Some of you might say, okay, let's put oxygen. So let's do a bit of thinking. Okay, let's do a bit of thought process. Let's put oxygen. Okay, then after I have oxygen here, then you'll be thinking, okay, this is an OCH3, like it's a match made in heaven. It's perfect already, perfect answer. I can agree with you for a while, okay, that this hydrogen is likely to be found close to 4 in that case. However, what is this question mark? What do you think this question mark is? So if you scrutinize, it cannot be nitrogen, you see. You cannot stick everything together, you know. Then, and remember that my ring system, right, my aromatic ring must be tri-substituted. Yeah. So the most likely candidate here would be the phenyl ring. Correct? So I'm just going to replace this question mark with a phenyl ring. So I'm going to change my color to blue. So I'm going to change it into a phenyl ring. Now, this is not going to be so simple anymore because if I have a phenyl ring, remember a phenyl ring, okay, let me go to this. If I have a phenyl ring, right, because I think most of you need a bit of guide from here. If I have a phenyl ring like this, I'm going to expect about 2 plus, 2 plus, 2 plus, right? And now I have, what do I have here? I have an oxygen. So I have a 2 plus, oxygen is about going to hit 4, so it's about 6. Even if I give it a 20%, 30% discount, it's going to, I will expect my H here to have a chemical shift of about 5. But it's not hitting 5, it's only hitting 4. Yeah, so therefore I need to change my structure a little bit. I hope you can agree with me. I need to change structure a bit. So I cannot have a OCH3 here. So I need to modify this. I can't have an OCH3. So what I can have would be an NCH3. Okay, an N methyl. Which makes more sense, right? And then I need to put in the H. Yeah, because the N will cause the chemical shift of this particular hydrogen being relatively electronegative but not as electronegative as oxygen. It will cause the electronegativity, I mean it will cause the hydrogen to hit chemical shift of about 3. Okay, or slightly below 3. And then with the phenyl ring coming in, I think it will hit about 4. Yeah, so this is kind of like the perfect picture that you need to paint, if you get what I'm trying to say. Okay, so therefore, one of the structural features I expect will be what I've drawn on the screen over here. Okay, and of course, if I'm just going to erase this to make life a bit easier, I would expect the broad hydrogens, okay, to be likely due to this particular proton. Okay, so now I already formulated a mono-substituted phenyl ring. Okay, and can I then put in my OCH3? Yes, my OCH3 is likely to be isolated. So therefore, can I just put my OCH3 here? Yes, I can. I'm just going to put my OCH3 here. And then finally, what am I left with? I'm left with this particular quartet and this particular triplet, which is definitely a match made in heaven because this is likely to be a CH2, CH3. And this being a CH2, CH3, what do you think is likely to be the question mark here? So you're only left with one choice, one option, which is the phenyl ring, right? And it does make sense because the chemical shift of this is about 2.7, 2.8. I think it makes perfect sense that my final substituent here is therefore a CH2, CH3. Okay, so I hope that by going through this exercise in this particular manner, although it's kind of messy, but you will kind of like get the thought process on how do you actually go about solving such problems. It's definitely not an easy task. You need experience. You realize that whatever I've said, it all came from I think for the teachers, 15, 20 years of experience. Some of us doing research, like we look at NMR every single day. So experience does help a lot in such problem solving. Okay, so I'm not going to go into details like how to write your NMR table, all this. I'm not going to go into that because I'm sure if you follow what we have in the lecture notes, in the sample solution to the tutorials, etc., you will be able to get it. Okay, I'm not also going to answer B1 about why the signal will disappear because I think most of you are quite good at it. Okay, so that will be the end of my debrief. So the main thing, as I said, the main focus here is actually on how do you actually base on the information and come up with a final structure. Some of you might be asking, is the substituent pattern important? No, I don't think it's important here. Yeah, because you guys are not trained to decide, whether is it 135, 123, or 145, that kind of substitution pattern. It doesn't really matter. Then you might be wondering, I think the final question that I think I didn't really answer earlier on is, why isn't it an alcohol? Yeah, I think I have indirectly answer it because I need an O methyl. So once I have an O methyl, then the alcohol is not possible. Okay, yep. So I hope you find this useful. Then do expect more of such debrief videos to come along the way.